So this first chapter, we're going to talk about oscillatory motion. It's partially a review. Mass on a spring, for example. Mass on a spring, if I displace the mass a little bit and let go, that mass is going to bounce up and down on the spring. Well, energy is still conserved. When I push the mass down to that lower distance, we had potential energy, elastic potential energy, energy stored in the spring. The spring starts pulling it up, so that potential energy starts turning into kinetic energy, so the motion of the mass, and potential energy, gravitational potential energy, because it's moving vertically. So energy, conservation of energy is still perfectly applicable. What we're going to look at that's new is we're going to look at describing the position of our mass at any point in time. So describe the motion as a function of time. If I could somehow attach a marker to the back of that mass and then have a piece of paper and move the piece of paper constantly at a uniform rate along, what would the graph look like? Sine or cosine? I'm sorry, that's supposed to be. So it oscillates with time, hence the term oscillatory motion. If there's no friction and no drag associated with the problem, the peak is always going to be the same. Okay? If there's no drag and no friction, there's no non-conservative force to take energy out of the system. The system will consist of potential and kinetic energy all the time. So a couple of terminology pieces. The distance from equilibrium to the peak, or the distance from equilibrium to the valley, that's called the amplitude. We use a capital A to represent it. So in this particular case, the amplitude represents the maximum distance our mass moves from equilibrium. Equilibrium is right there. The resting state, where there would be no motion at all. The amplitude is determined by me. I'm the one that pushes down, I'm the one that displaces it, and lets go. So I determined the amplitude of this motion by how far I moved it and pushed it downwards. By the way, on our graph, the vertical axis is the position of the object. The horizontal axis is time. So if we were to measure from peak to peak, that would be the amount of time to go from the highest point all the way down back to the highest point. That would be considered the period. The amount of time to complete one cycle is the period. We use a capital T specifically to represent period. So capital T, we used it before when we dealt with orbits. Capital T was the time to complete one orbit. Capital T period now is the time to complete one oscillation. So to get from one point back to the exact same point. We could represent it from valley to valley. That would be fine too. Now another term that we'll use is frequency. Frequency is the rate at which the object is oscillating at. Frequency is the number of oscillations or cycles per second. So the number of times it bounces up and down in 1 second. Frequency and period are just inversely related to each other. Period is the amount of seconds it takes to complete one cycle. Frequency is the number of cycles completed in 1 second. So they're just inversely related to each other. Okay? One other term we're going to use, which we're already somewhat familiar with, is called the angular frequency. I want you to imagine I had a wheel. So a big wheel that we could spin. And I had a peg sticking out on the wheel. So that wheel rotating at a uniform rate. Imagine if I turned the wheel so all you could see was the peg. So the wheel is now oriented this way. You can't see the face of the wheel anymore. All you can see is the peg. The peg's still making a circle, but it's hard for you to tell that it's making a circle. The overall motion that you see is analogous to the bouncing up and down of the mass. The faster I do this, I start matching up with that. So even though this is moving on a circle, you still see the up and down motion that looks just like the mass. Angular frequency is the angular speed that wheel would have to turn at to match the mass bouncing up and down. Okay? So it's omega. It has units of radians per second. We call it angular frequency in this case, but it's still a speed, angular speed, in terms of how fast it would have to move on a circle to match the motion of the mass on the spring. Omega and frequency F are directly related. It's just a difference of units. This is number of oscillations per second. This is number of radians per second. So it's simply a unit conversion from one oscillation. One oscillation would be 2 pi radians. So converting between regular frequency. By the way, oscillations per second is also called a hertz. We use a capital H with a lowercase z. Hertz spelled like the car company, the rental car company, H-E-R-T-Z. Okay. So our equation that describes the motion of our mass on our spring as a function of time, sinusoidal. Technically, if we started measuring at the instant I let go of that mass, I should have graphed it starting down here. Because I pushed it down and let go, so it started at a maximum negative value. Negative cosine graph. The one I sketched on the board started at 0 and it was already moving. Sine graph. Generically, the position of our object as a function of time looks like this. Capital A, amplitude. Capital A is the maximum distance our mass moves from its equilibrium position. Now, you can write it as a sine or cosine graph. You just need to know which is the appropriate case for the problem. Okay. Omega t is an angle. Omega t is the angle in radians that our object is at. Omega is the angular frequency, so the rate at which it is oscillating at in radians per second. T is whatever time you happen to be interested in. Phi naught, that's called a phase shift. Phi naught makes sure that your function accurately describes your graph. For example, this red one I sketched in. If we were to write it as just cosine, a positive cosine function, this red one that I sketched in is not a positive cosine function. You right with that? If I want to graph cosine, positive cosine function, it starts at a positive maximum value and goes down. This one's starting at a negative maximum value and going up. So what is the difference in radians between starting at a maximum and the minimum? Pi. So phi naught would be pi. So we would write this as a cosine omega t plus pi. So phi naught is just making sure that your graph is matching your function. What about cosine versus starting at 0? Perhaps. Exactly right. Now, you can go ahead and not use the phi naught and write it as a negative cosine. That's perfectly fine too.